an object so powerful, so dense, that nothing, not even light, can escape its grasp. Black holes lurk in the depths of space with an insatiable hunger for anything that comes too close. They are invisible giants, silently bending space and time, swallowing stars, and reshaping entire galaxies. Their presence can be felt across the cosmos, including our own Milky Way. Let's journey into the heart of these cosmic monsters, exploring the different types of black holes and their strange properties with real-life examples that defy belief. From the massive black hole at our galaxy center to the mysterious phantom black holes drifting in space. By the end, you'll see why black holes are some of the most feared and fascinating objects in the universe. The enigmatic stellar black holes, born from dying stars. Black holes have a way of capturing our imagination. They were once just theoretical predictions, but over the years, astronomers have uncovered more and more evidence that black holes are very real, and they're scattered throughout our universe. These cosmic giants form when massive stars run out of fuel and collapse under their own gravity, compressing all their matter into a single point known as a singularity. The singularity is a place of infinite density and gravity so intense that all matter is crushed into an unimaginably small space. Around this point lies the event horizon, a boundary where gravity is so strong that not even light can escape. Beyond the event horizon, scientists can only speculate on what truly happens. Some suggest that everything that falls into a black hole is compressed to a single point, crushed to an infinite density at the singularity. Others believe that black holes might be connected to wormholes that lead to other parts of the universe, or even to different universes altogether. All we know is that once something crosses that invisible line, it's beyond our reach. Once anything crosses the event horizon, whether it's a beam of light, a planet, or even a star, it's lost forever. Our best scientific theories, like Einstein's theory of relativity, explain how gravity works on a large scale and predict the formation of black holes. But when it comes to the singularity, these theories start to fall apart. At this level, our understanding of physics breaks down completely, and the usual laws of nature no longer apply. It's as if black holes exist as a kind of wall in our knowledge. Black holes come in various sizes, from stellar black holes a few times more massive than our sun, to supermassive black holes that weigh billions of times more. These supermassive giants sit at the heart of galaxies, shaping the lives of stars and planets around them. Black holes can feed on nearby stars and matter, growing larger and more powerful over time. Stellar black holes, though only one type in the wide spectrum of black holes, are some of the most iconic and well-studied. When a massive star, one with at least 8 times the mass of our sun, reaches the end of its life, it undergoes a transformation that's as violent as it is final. For millions of years, these stars burn hot and bright, fusing hydrogen into helium and then into heavier elements, with the force of nuclear fusion pushing outwards against the force of gravity. But eventually, they reach a point where they can no longer sustain this fusion process. With no more fuel to burn, the outward pressure disappears, and gravity takes over completely. The core collapses inward under its own weight, and in a fraction of a second, it becomes so dense that a black hole is born, and the rest of the star is blown outward in an explosion called a supernova that can briefly outshine entire galaxies. But what's left behind is a darkness so powerful that nothing can escape it. The newly formed black hole may start small, but as it consumes nearby gas, dust, and sometimes even entire stars, it grows, becoming more massive and increasing the size of its event horizon. These stellar black holes vary in size, but they generally contain about 3 to 10 times the mass of our sun. Even though they are relatively small compared to supermassive black holes, their gravitational pull is still powerful and far-reaching. In some cases, stellar black holes exist alone in space, unnoticed and undetectable, without any nearby material to reveal their presence. But in other cases, a stellar black hole has a partner, a nearby star that it orbits. When a black hole and a star orbit each other, The immense gravity of the black hole can start to pull matter off the star. This material spirals inward, forming an accretion disk, a swirling, glowing ring of gas and dust that heats up to extreme temperatures as it approaches the black hole. From a distance, these systems appear as bright X-ray sources, which can be detected by telescopes here on Earth. Observing these X-rays allows scientists to study the black hole's behavior and even estimate its mass. These X-ray binaries, as they're called, are some of the best evidence we have for the existence of stellar black holes. The intense light they produce reveals details about the speed and pattern of the material spiraling inward, which in turn provides insights into the physics of the black hole itself. The intense gravity of a stellar black hole creates a gravitational well in space, bending the paths of nearby objects. A planet orbiting close to a black hole would experience strong gravitational tides, stretching and squeezing as it moved through the uneven gravitational field. If a planet ventured too close, it could be torn apart entirely, its debris spiraling into the black hole in a final violent encounter. Fortunately, such events are rare, and most stellar black holes drift through space far from any potential victims. In some galaxies, stellar black holes are scattered throughout the arms and disks, hidden among billions of stars. Their influence on their galactic neighborhoods may be small, but each one represents the endpoint of a massive star's life, a kind of cosmic gravestone marking where a sun once burned bright. Stellar black holes remain largely the same size as when they formed. This makes them stable, enduring objects that can drift through space unchanged for eons, holding on to the secrets of their formation. In the vast expanse of space, some stellar black holes may even drift alone, completely undetectable. These quiet black holes pose a special challenge to astronomers, because without an accretion disk or a partner star, they don't produce any detectable radiation. They are truly invisible, their presence inferred only by their gravitational effects or, in some cases, by the bending of light from distant stars behind them. This phenomenon, known as gravitational lensing, occurs when a black hole passes between us and a distant star, acting like a magnifying glass and distorting the star's light. By observing these distortions, scientists can sometimes infer the presence of a stellar black hole, even if it is otherwise hidden. In some cases, stellar black holes can merge with each other or with neutron stars, creating gravitational waves that ripple across space. These waves, first detected in 2015, have opened up a new way of studying the cosmos, allowing scientists to observe collisions between black holes directly. Each merger is like a seismic event in space, a brief but powerful release of energy that echoes across the universe. These mergers are rare, but when they happen, they offer a unique opportunity to learn about black hole properties, such as their mass and spin. Intermediate black holes, the missing links of the universe. Intermediate black holes, sometimes called the missing links of the cosmos, occupy a unique space in the black hole family. These black holes are neither as small as stellar black holes, nor as massive as the supermassive black holes that lie at the centers of galaxies. Instead, they sit in between, with masses ranging from hundreds to thousands of times that of our Sun. Despite their predicted existence, finding and studying intermediate black holes has proven to be incredibly challenging. If intermediate black holes do exist, they might act as stepping stones between small stellar black holes and the massive giants that dominate the centers of galaxies. The idea is that over time, smaller black holes could merge or gather enough material to grow into intermediate sizes, which might eventually lead to the formation of supermassive black holes. But if that's the case, why are they so hard to find? Shouldn't the universe be full of these mid-sized black holes, especially in the bustling areas of space where galaxies collide or where many stars are packed together? One of the biggest challenges in finding intermediate black holes is that they are not as active as their larger counterparts. Supermassive black holes often have huge accretion disks of gas and dust swirling around them, emitting vast amounts of light and energy that make them visible even across large distances. But intermediate black holes, especially if they are isolated or in quieter parts of space, might not have enough surrounding material to create this same type of brilliant display. Without an accretion disk or bright X-ray signals, an intermediate black hole would be almost invisible, blending into the background of space and eluding our telescopes. However, there are some indirect ways to detect these elusive objects. One of the primary methods is by looking for gravitational effects. When an intermediate black hole passes near a star or a cloud of gas, its gravity can cause subtle shifts in the objects around it. Astronomers can sometimes spot these disturbances by watching for changes in the orbits of stars or the shape of gas clouds. Another method involves looking for gravitational waves that are produced when black holes merge. If a stellar black hole were to collide with an intermediate black hole, the event would create gravitational waves strong enough to be detected by observatories on Earth. These waves would offer hints about the sizes and locations of intermediate black holes, even if we can't see them directly. Despite the difficulty in detecting them, there have been a few promising candidates for intermediate black holes. One well-known case is a black hole found in the dense star cluster known as Omega Centauri, located in our own galaxy. This cluster contains hundreds of thousands of stars packed tightly together, making it a prime location for black holes to form. Some observations have suggested that Omega Centauri may contain an intermediate black hole several thousand times the mass of our Sun at its center, exerting gravitational influence on the surrounding stars. While the evidence isn't conclusive, it gives scientists hope that intermediate black holes might be lurking in other, similar star clusters. In the galaxy M82, astronomers observed a powerful X-ray source that appeared too bright to be caused by a stellar black hole, but was too small to be a supermassive black hole. This object, named M82X1, could be an intermediate black hole, shining brightly as it consumes material from a nearby star. The clearest evidence, however, comes from GW 190521, a gravitational wave signal from 2019, which indicated that about 17 billion light-years away, an 85 solar mass black hole had merged with one that was 66 solar masses, resulting in the formation of a 142 solar mass black hole. This new black hole was about 9 solar masses, smaller than the combination of the two, because that mass was released as energy in the form of gravitational waves. The importance of intermediate black holes goes beyond simply filling in the gaps in black hole sizes. These mid-sized objects could play a crucial role in shaping galaxies. If intermediate black holes exist in the centers of star clusters or small galaxies, they could help to merge and organize the surrounding stars, contributing to the overall structure of galaxies. When galaxies collide, intermediate black holes from each galaxy could eventually find each other, merging and potentially leading to the formation of a supermassive black hole in the merged galaxy's center. The process of galaxy formation and evolution is still a major mystery in astrophysics, and intermediate black holes might be one of the missing pieces. If these black holes were more common in the early universe, they could have provided the seeds for today's supermassive black holes. The early universe was a chaotic place, full of young, massive stars and dense gas clouds that could have easily created intermediate black holes through frequent collisions and star deaths. Over billions of years, these intermediate black holes could have grown by consuming gas and merging with each other, gradually forming the supermassive black holes we see today. Supermassive black holes, giants of the galactic core. Supermassive black holes are the true giants of the universe. They dominate the centers of galaxies, including our own Milky Way. These enormous black holes can weigh millions or even billions of times more than our Sun. Their sheer size and power make them some of the most influential objects in the cosmos, not just for their gravity, but for the way they shape entire galaxies and help us understand the broader story of cosmic evolution. Every large galaxy that astronomers have studied in detail seems to have a supermassive black hole at its core. The Milky Way, for instance, hosts a black hole called Sagittarius A*, which has a mass of about 4 million times that of the Sun. Other galaxies contain black holes that are even larger. The galaxy M87, for instance, holds a supermassive black hole with a mass estimated to be about 6.5 billion times that of the Sun, making it one of the most massive black holes we've observed. This M87 black hole was also the first ever black hole to be imaged in 2019 through data gathered from the Event Horizon Telescope. Despite their incredible mass, supermassive black holes don't simply sit at the centers of galaxies without influence. Instead, they play an active role in shaping the structures of the galaxies around them. One of the ways they do this is by controlling the flow of gas and stars in their neighborhoods. Because of their intense gravitational pull, they can gather material from their surroundings, creating accretion disks that can glow so brightly that they outshine entire galaxies, creating what astronomers call active galactic nuclei, or AGNs. When viewed from far away, an active galaxy looks like a single bright spot with jets of radiation streaming from its center, a sign that its supermassive black hole is actively consuming material. These jets are some of the most powerful features associated with supermassive black holes. As material falls toward the black hole and heats up, some of it is expelled in two opposite directions, forming jets that travel at nearly the speed of light. These jets can extend for thousands of light years, pushing through the surrounding galaxy and even beyond into intergalactic space. The force of these jets is so intense that it can clear out gas from large regions of the galaxy, halting star formation in those areas. In this way, supermassive black holes act as regulators of galactic growth, controlling how much gas is available for new stars and shaping the distribution of stars within the galaxy. Some theories suggest that galaxies and their central black holes grow together, influencing each other over billions of years. When a galaxy is young and filled with gas, it can produce new stars at a rapid rate. But as the central black hole grows, its jets and radiation start to heat up and blow away the surrounding gas, gradually slowing down star formation. This feedback loop could be what allows galaxies to reach a stable size, with the black hole acting as a kind of galactic thermostat, preventing runaway growth. The exact process by which supermassive black holes form is still one of the biggest mysteries in astrophysics. There are a few leading theories, but none have been fully confirmed. One idea is that these black holes grew from the merger of many smaller black holes over time, a process that could have started in the very early universe when the first stars and galaxies were forming. Another theory is that supermassive black holes formed directly from massive clouds of gas that collapsed under their own gravity, creating a black hole from scratch without the need for a star. This second theory is particularly intriguing because it suggests that some black holes may have existed in the early universe, even before the first stars had a chance to explode and create stellar black holes. By studying the light from distant quasars, galaxies with extremely bright active nuclei, we can see supermassive black holes as they appeared billions of years ago, back when the universe was young. These quasars allow us to trace the history of black holes and galaxies, helping us understand how structures formed and evolved over time. Some quasars are so far away that the light we see from them today began its journey across the universe, when the universe itself was only a fraction of its current age. Ultramassive black holes, when supermassive just isn't enough. When it comes to black holes, the word supermassive might seem like the ultimate descriptor, but in the cosmos, there are a few black holes that go beyond even that category. These rare, extraordinary entities, known as ultramassive black holes, stretch the boundaries of what we understand about mass, gravity, and the formation of cosmic structures. Ultramassive black holes are defined as black holes with masses exceeding 5 billion times that of our Sun, and in some cases, they reach 50 billion solar masses or more. The scale of these objects is almost unimaginable, and they challenge astronomers to rethink not only the upper limits of black hole mass, but also how such behemoths could form in the first place. One of the first questions that arise when considering ultramassive black holes is, how do they grow to such astonishing sizes? For black holes of this mass, the typical growth methods we know of, merging with other black holes, or gradually accumulating gas from the galaxy around them, are not quite sufficient to explain their sheer size. Mergers between black holes are rare and occur over incredibly long timescales, so accumulating billions of solar masses in this way would take far longer than the age of the universe. Similarly, the material in a galaxy is finite, meaning that even if an ultramassive black hole were to consume gas and dust at a steady rate, it still wouldn't grow quickly enough to reach these immense sizes within the lifespan of the universe. Some scientists theorize that ultramassive black holes may have had a head start in the early universe. According to one hypothesis, these colossal black holes may have started as primordial black holes, formed shortly after the Big Bang, when the universe was much denser and more chaotic. If such primordial black holes existed, they could have grown rapidly by consuming large amounts of gas in the early universe, allowing them to reach ultramassive sizes within a relatively short period. Another possibility is that ultramassive black holes are the result of extreme galactic mergers. When two large galaxies collide, their central black holes often merge as well. In rare cases, multiple mergers involving galaxies that each contain supermassive black holes might lead to the creation of an ultramassive black hole. These events are rare, and for an ultramassive black hole to form, the conditions would need to be just right. A series of galaxy collisions, each one adding to the central black hole's mass, might allow a black hole to grow to an ultramassive size over billions of years. These ultramassive black holes would be found in the largest galaxies and galaxy clusters, where the environment is dense enough to support such growth. Currently, only a few ultramassive black holes have been detected, and they tend to exist in the most massive and densely populated regions of the universe. One well-known example is the black hole TON 618, located in a galaxy about 11 billion light-years from Earth. TON 618 is estimated to have a mass of around 40.7 billion solar masses, making it one of the largest black holes ever discovered. Since it is an active galactic nucleus, it emits a great deal of light, so much so in fact that the surrounding galaxy is outshone by it, and hence is not visible to us. It is 140 trillion times brighter than our Sun, making it one of the brightest known objects in the universe. We know that black holes feed on surrounding matter, pulling in gas and dust as they grow. However, if a black hole becomes too massive, it can actually begin to interfere with its own growth. The intense energy released as gas falls into the black hole heats up and pushes material away, creating a feedback effect. This feedback can drive gas away from the center of the galaxy, limiting the amount of material that can fall into the black hole. This effect is so powerful that it's often thought to be responsible for limiting the size of supermassive black holes. But ultramassive black holes suggest that, somehow, a few black holes have managed to overcome this limit and keep growing, defying the feedback process that usually restricts their size. The effects of ultramassive black holes extend far beyond their immediate surroundings. Because of their mass, they have an enormous gravitational reach, influencing stars, gas, and even other galaxies. In galaxy clusters, the presence of an ultramassive black hole at the center can shape the behavior of nearby galaxies. The black hole's powerful gravitational pull can hold the cluster together, preventing galaxies from drifting away and keeping the cluster's structure intact. Ultramassive black holes also produce massive jets of energy, similar to supermassive black holes, but on an even grander scale. These jets can extend far beyond the galaxy, heating gas in the surrounding area and affecting star formation in neighboring galaxies. In this way, ultramassive black holes act as cosmic architects, helping to shape the structure and evolution of galaxy clusters. As we develop more powerful telescopes and observatories, our ability to detect and study ultramassive black holes is expected to improve. Future missions may allow us to see these giants in greater detail, observing their interactions with surrounding galaxies and the effects of their immense gravitational fields. Primordial black holes, ghosts from the dawn of the universe. Unlike black holes that form from the collapse of massive stars, primordial black holes are believed to have formed in the earliest seconds of the universe, created directly from the extreme conditions of the early cosmos. At that time, the universe was incredibly compact, with energy and matter packed so tightly that tiny fluctuations in density could have led to areas with enough gravitational pull to collapse in on themselves, forming black holes. These hypothetical black holes, known as primordial black holes, would have been born without needing stars, existing as relics from a period long before galaxies, stars, or even atoms as we know them, came into being. Primordial black holes offer a potential answer to some of the universe's biggest mysteries. One of these mysteries is the origin of dark matter. Dark matter is a form of matter that does not emit light, making it invisible and undetectable by conventional telescopes. Scientists know that dark matter exists because its gravitational influence can be seen affecting galaxies and galaxy clusters. Without dark matter, galaxies would lack the mass needed to hold their stars together, and entire galaxy clusters would lack the gravitational glue needed to bind them. But despite decades of study, scientists have yet to identify what dark matter is made of. Some scientists think primordial black holes might be a solution to the dark matter mystery. If a large number of these black holes formed in the early universe, they could be scattered throughout the cosmos, creating a network of dark objects that exert gravitational forces on visible matter. Unlike the regular matter that makes up stars, planets, and galaxies, these primordial black holes wouldn't emit any light. They would be, in effect, dark objects, matching the behavior of dark matter. If primordial black holes do exist and make up a significant portion of dark matter, it would mean that dark matter isn't made of exotic particles, as many scientists have previously assumed, but instead of ancient black holes left over from the early universe. Primordial black holes would be much smaller than the black holes we are used to thinking about, possibly with masses ranging from that of a small asteroid to several times the mass of the Sun. Unlike larger black holes, which influence their surroundings by pulling in nearby gas and dust, smaller primordial black holes would be nearly invisible, interacting only through their gravitational pull. This makes them challenging to observe directly. However, there are some ways to infer their presence. For instance, scientists can search for tiny distortions in the light from distant stars, indicating the gravitational influence of a small, invisible black hole passing in front of them. This technique, known as gravitational microlensing, can reveal the presence of compact objects that would otherwise go unnoticed. In the early universe, matter was distributed more or less evenly, but slight irregularities eventually led to the clumping of gas, which formed the first stars and galaxies. The presence of primordial black holes could have acted as seeds for these structures, providing gravitational centers around which matter could gather. Over time, these seeds would have attracted more gas and dust, leading to the birth of stars and galaxies. In this way, primordial black holes could have helped shape the universe as we know it, guiding the formation of the first galaxies and setting the stage for the cosmic landscape we observe today. Without some kind of seed to initiate the formation of galaxies, it's difficult to understand how cosmic structures could have emerged as quickly as they did after the Big Bang. If primordial black holes were present, they would have acted as catalysts, providing the gravitational anchor points needed to draw in matter and accelerate the process of galaxy formation. This theory aligns with observations showing that galaxies began forming relatively soon after the Big Bang, suggesting that some kind of gravitational scaffolding may have been in place to guide their development. But while primordial black holes offer fascinating explanations for dark matter and galaxy formation, their existence remains hypothetical. The search for primordial black holes has led scientists to explore a variety of methods, from gravitational wave detectors to cosmic microwave background studies. Gravitational wave observatories like LIGO and Virgo which have already detected mergers between larger black holes, could potentially pick up signals from merging primordial black holes as well. However, such events would likely be much rarer and fainter than those produced by larger black holes. Scientists are also studying the cosmic microwave background, the faint glow of radiation left over from the Big Bang. If primordial black holes were abundant in the early universe, they could have left subtle imprints on this background radiation, altering its structure in ways that might still be detectable today. Rogue black holes, wandering dangers in the galactic void. Rogue black holes are not bound to any specific location, but move through the galaxy with little regard for what lies in their path. These objects, though potentially smaller in scale than their supermassive counterparts, are nevertheless capable of decimating anything that crosses their trajectory. Stars, planets, even entire solar systems could face disruption if one of these rogue black holes were to drift close enough. Rogue black holes are thought to form when a black hole gets ejected from its home galaxy or star cluster, often as a result of powerful gravitational interactions. One common cause of such an ejection is the merger of two black holes. When two black holes come together, the final merger can release intense gravitational waves that carry energy away from the system. This loss of energy can send the resulting black hole hurtling in a random direction, effectively ejecting it from its original location. Another possible cause is when a black hole forms from a star that is part of a binary system. If one star collapses into a black hole while the other remains intact, the gravitational relationship between the two might break, sending the black hole on a wandering journey through space. Once a black hole is on the move, its journey is governed by the natural orbits and motions of galaxies and star clusters. Some rogue black holes may eventually find new homes, settling into orbits around other stars or entering different star clusters. Others, however, may wander for billions of years without encountering anything substantial. In the vastness of space, it's entirely possible for a rogue black hole to travel undisturbed through interstellar space, far from stars, planets, or other celestial bodies. But on occasion, a rogue black hole could stray close to a solar system, disrupting or even destroying any planets or stars within range. If a rogue black hole were to enter our solar system, the results could be devastating. The black hole's gravity would cause major disturbances, potentially altering the orbits of planets or drawing gas and dust from nearby stars. For a black hole that's only a few times the mass of our Sun, such an encounter might start with distant gravitational effects, with the outer planets experiencing changes in their orbits. But as the black hole gets closer, its influence would grow stronger, and eventually it could reach a point where planets are pulled from their paths altogether or even swallowed by the black hole. For a system like ours, a rogue black hole would be a serious threat, even if it never came close enough to Earth. The disruption to the gravitational balance would throw planets, asteroids, and other bodies into new, unpredictable paths, causing chaos on a cosmic scale. One of the most unsettling aspects of rogue black holes is their stealth. Unlike stars, which emit light, black holes are nearly invisible. They don't radiate light or other forms of electromagnetic energy, making them difficult to detect unless they interact with nearby matter. The only way we'd notice it is if it began to pull on the system with its gravity, causing stars or planets to shift in their orbits. In cases where rogue black holes are actively consuming matter, they may become detectable. As a black hole feeds on gas or dust, this material can form an accretion disk around the black hole, heating up and emitting light as it spirals inward. But in the emptiness of interstellar space, where there is often little or no material to consume, a rogue black hole could remain entirely undetectable until it comes disturbingly close. Astronomers believe there may be millions of rogue black holes scattered throughout our galaxy, but spotting them is challenging. Some methods, like gravitational microlensing, have been used to detect a few potential rogue black holes, but it requires precise alignment and timing. The vastness of space means that the chances of a rogue black hole crossing paths with a populated star system alone. But the possibility is there. Hyper-energetic quasars, unleashing black hole fury across the cosmos. Quasars are among the most powerful and luminous objects in the universe, so brilliant they can outshine entire galaxies. They are born from supermassive black holes that are actively consuming enormous amounts of material. This relentless consumption fuels a process that transforms these black holes into cosmic beacons, illuminating the dark depths of space with intense energy. The material falling toward the black hole first forms an accretion disk. As this material spirals inward, it gets compressed and heated to extreme temperatures, releasing vast amounts of light and other forms of energy. This energy is what makes quasars so bright. In some cases, a single quasar can shine hundreds of times brighter than an entire galaxy, allowing astronomers to observe them from billions of light years away. The intense brightness of quasars isn't just due to visible light. They emit energy across nearly the entire electromagnetic spectrum, from radio waves to X-rays and even gamma rays. This wide range of energy output makes quasars visible to different types of telescopes, each capturing different parts of the radiation they emit. This broad energy range shows that quasars are not just bright, but also incredibly energetic, releasing more power in a single second than our sun will emit over billions of years. Quasars often generate powerful jets that shoot out from their poles. These jets are made up of charged particles accelerated to nearly the speed of light, and they can extend for hundreds of thousands, even millions, of light years beyond the host galaxy. The energy carried by these jets interacts with gas, dust, and other galaxies in the surrounding region, creating shock waves and influencing the evolution of galaxies nearby. The jets can be powerful enough to push material out of the galaxy, halting star formation by removing the gas needed to form new stars. The jets from a quasar can also heat up intergalactic gas, preventing it from cooling and collapsing to form stars. In this way, quasars can suppress star formation, not only in their own host galaxies, but also in nearby galaxies, effectively sterilizing parts of the universe. Because they are so bright, quasars can be observed across vast distances, allowing scientists to look back billions of years in time. The light we see from distant quasars began its journey long before our sun or solar system even existed, providing a direct window into the early universe. By studying quasars at different distances, astronomers can trace the evolution of galaxies and black holes over cosmic history, piecing together how the first black holes formed, grew, and influence their surroundings. While quasars are mostly observed in distant galaxies, there was a time when they were more common in the universe. In the early stages of the universe, galaxies were closer together and full of gas, creating the ideal conditions for black holes to feed and generate quasars. Over time, as galaxies evolved and their central black holes consumed nearby material, quasars became less common, giving way to quieter galaxies like our own Milky Way. Today, most quasars we observe are billions of light years away, meaning we're seeing them as they were in the distant past. If a quasar were to flare up in a galaxy relatively close to ours, the intense radiation could have serious consequences for nearby star systems, potentially even affecting planets. The gamma rays and other high-energy radiation emitted by quasars could strip away atmospheres or disrupt the chemical processes necessary for life. Fortunately, most active quasars are far from our galaxy. The amount of material required to fuel a quasar is immense, raising questions about how such large amounts of gas and dust accumulate and feed the black hole over time. The physics of the jets produced by quasars also remains an area of active research, as scientists try to understand how particles are accelerated to such extreme speeds, and what role magnetic fields play in the process. Quasars serve as powerful examples of how black holes, despite their name, can be some of the brightest and most dynamic objects in the universe. Blazars, when black holes point their cosmic beams at Earth. Blazars are a unique and extreme type of active galactic nucleus. What sets blazars apart is the alignment of their powerful jets, which are directed almost precisely toward Earth. This alignment makes blazars appear especially bright to observers on Earth. This direct line-of-sight alignment allows us to see details of their energetic processes that are hidden in other galaxies. The intense brightness of blazars comes from the supermassive black hole at their core, which pulls in massive amounts of gas and dust from the galaxy around it. But it's the jets streaming from the poles of the black hole that make blazars so remarkable. These jets are composed of charged particles like electrons, accelerated to near the speed of light by powerful magnetic fields generated by the black hole's spin. As these jets point directly at Earth, they become concentrated and amplified, creating what scientists call a relativistic beaming effect. This effect is like shining a flashlight directly into an observer's eyes. It makes the blazar appear brighter and more energetic than it would if the jet were oriented away from us. These powerful jets emit radiation across the entire electromagnetic spectrum, producing waves of energy that can be detected by various types of telescopes, including radio, optical, and gamma-ray observatories. The energy output of blazars is so great that they can fluctuate rapidly, with bursts and flares that vary in brightness from day to day or even minute to minute. These flares are driven by turbulence and collisions within the jet as particles slam into each other and release energy. The cause of these eruptions is still not entirely understood, but they likely involve sudden shifts in the magnetic fields surrounding the black hole, leading to explosions of energy that send powerful waves of radiation toward Earth. The radiation emitted by blazars includes gamma rays, the most energetic form of light. Gamma rays are dangerous because they have enough energy to penetrate matter and disrupt atoms, breaking apart molecules and creating harmful particles. When blazars flare up, they send streams of gamma rays into space. If Earth were close enough to an active blazar, the radiation could have serious effects on our planet, stripping away parts of the atmosphere or disrupting life by interfering with biological processes. Fortunately, the nearest known blazars are far enough away that their gamma rays disperse and weaken long before reaching us. However, studying the impact of this intense radiation allows scientists to understand the potential hazards that similar processes could pose if they occurred closer to home. Blazars don't just emit light, they also send out high-energy particles known as cosmic rays. These cosmic rays, accelerated to incredible speeds by the magnetic fields in the jets, are some of the fastest-moving particles in the universe. When they reach Earth, they collide with particles in our atmosphere, creating showers of secondary particles that can be detected on the ground. Cosmic rays from blazars provide valuable information about the composition and behavior of the jets. However, cosmic rays are also a form of radiation that, in high doses, can be harmful. The brightness and variability of blazars make them ideal natural laboratories for studying high-energy physics, helping researchers to refine models of how black holes interact with their surroundings. Event horizon collisions. What happens when black holes merge? When two black holes come close enough to each other, they enter a cosmic dance that will ultimately end in a dramatic collision. These collisions between black holes are among the most powerful events in the universe, releasing vast amounts of energy in the form of gravitational waves. Gravitational waves are ripples in the very fabric of space and time, traveling outward like waves in a pond. The collision of black holes, an event of such intense gravity, twists and stretches space itself. As the two black holes spiral toward each other, they accelerate and gain energy, moving faster and faster. This process, known as in-spiral, is where most of the gravitational waves are generated. The strength of these waves increases as the black holes get closer and the frequency of the waves rises. These gravitational waves carry information about the black holes, such as their masses, spins, and the distance between them, allowing scientists to study the black holes indirectly. The waves travel across billions of light years, reaching Earth with only a tiny fraction of their original strength. But sensitive detectors like LIGO and Virgo can pick up these faint signals. At first, the two black holes orbit each other at a distance, but as they spiral inward, they fall closer and closer, and the gravitational waves they emit grow more intense. The closer they get, the stronger their gravitational fields merge, distorting space-time more severely. This rapid acceleration creates an almost deafening surge in gravitational waves, an indication that the two black holes are on the verge of colliding. At the moment of impact, they combine their masses into a single, larger black hole, unleashing a powerful burst of gravitational waves that ripples across the universe. The final moment before the merger is called the ring-down phase, where the single, newly formed black hole releases a last intense wave of gravitational energy before settling down. The energy released during this phase can be greater than the energy emitted by all the stars in a galaxy combined, but it only lasts for a fraction of a second. This new, larger black hole is less massive than the combined mass of the original two black holes. This is because a small portion of their combined mass is converted directly into gravitational wave energy and released into space. With gravitational wave astronomy, scientists have a new way to hear black holes in action. Each collision adds to our knowledge of the universe, confirming Einstein's predictions about gravity and space-time, and giving us clues about how black holes form and grow. As two black holes collide, they bring with them their individual spins and angular momentum. This means the merged black hole might spin very rapidly, creating one of the fastest rotating objects in the universe. This high rotation speed can distort the shape of the new black hole, flattening it slightly at the poles. Some researchers believe that if the merged black hole spins fast enough, it could even create jets of particles, similar to quasars, although this remains a theoretical idea. The merging of black holes is a truly chaotic process. Surrounding material, if there is any, could be pulled in and heated up by the intense gravitational fields, potentially creating flashes of light or other electromagnetic signals that scientists could detect. However, since black holes are often found in areas with little gas or dust, these events are usually dark and invisible, except for their gravitational waves. Gravitational waves from black hole mergers have also taught us about the size and distribution of black holes in the universe. When scientists detect these waves, they can measure the mass and size of the colliding black holes, revealing patterns about how and where black holes form. Some black holes are much heavier than others, suggesting they may have already merged with other black holes in the past. In dense environments, such as star clusters, black holes could merge repeatedly, forming progressively larger black holes over time. These hierarchical mergers create a cycle of growth, possibly contributing to the formation of supermassive black holes found at the centers of galaxies. When two black holes collide, their event horizons stretch and merge, creating a new, larger event horizon. Scientists are still studying what happens at this boundary, as the collision creates an incredibly complex and turbulent area of space-time that is difficult to understand. According to some theories, this surface where the two event horizons meet might briefly create intense gravitational effects, possibly even affecting the way gravitational waves are emitted. Some theories suggest that if two black holes of extreme mass were to collide, they could briefly create a naked singularity, an area where gravity becomes infinitely strong without the protection of an event horizon. The elusive, recoiling black holes, when black holes are ejected from galaxies. Sometimes, when two black holes merge, the force of their collision is so intense that the newly formed black hole doesn't stay put in its original location. Instead, it can be kicked out of the center of the galaxy it once belonged to, sent hurtling through space like a cosmic wanderer. These are called recoiling black holes. To picture it, imagine two massive whirlpools in the ocean merging, creating such a strong surge of energy that the new, larger whirlpool is flung outward. That's essentially what happens to recoiling black holes. When black holes merge, they release an intense burst of gravitational waves. But if the black holes are of different sizes, or if they're spinning in different directions, the gravitational waves they emit can become uneven. It's like a rocket blasting off. When the forces acting on it aren't balanced, it gets pushed in one direction. In the case of merging black holes, the imbalance in gravitational waves creates a powerful kick, sending the new black hole off at incredible speeds. This kick can be so strong that it overcomes the gravitational pull of the galaxy, ejecting the black hole into intergalactic space. Evidence for recoiling black holes comes from observations of the centers of galaxies where a supermassive black hole should be present, yet appears to be missing. In these cases, astronomers speculate that the black hole was ejected after a merger. In a few cases, scientists have spotted strange luminous trails thought to be recoiling black holes pulling along a stream of gas or stars as they leave their galaxies behind. Depending on the strength of the gravitational wave kick, a recoiling black hole could travel through space at speeds of thousands of kilometers per second. This velocity is fast enough to escape not only the core of the galaxy, but even its outer regions. Once it escapes, the black hole is left to drift through intergalactic space. There, the recoiling black hole would likely continue to pull in any gas or dust it encounters, but without the rich environment of a galaxy, it would appear mostly invisible, nearly impossible to detect directly. Without a central black hole, the galaxy loses a powerful gravitational anchor. This can lead to changes in the movement of stars, as well as the distribution of gas and dust, ultimately affecting the galaxy's future shape and development. In some cases, the galaxy may eventually attract another black hole, but until then, it may lack the typical features of a galaxy with an active, central, supermassive black hole. The rarity of these events means that recoiling black holes are difficult to study, and so far, astronomers have only indirect evidence of their existence. What happens to these black holes over long stretches of time? Do they eventually slow down or settle into new locations? Could they influence the formation of new galaxies, or will they remain as isolated points of intense gravity in the emptiness of space? X-ray beacons of doom, black holes as powerful cosmic lighthouses. Some black holes become powerful sources of X-ray emissions, illuminating the dark cosmos with radiation that travels across vast distances. These X-ray beacons can be incredibly intense, providing a way for astronomers to detect black holes that would otherwise be invisible. These X-rays are produced when friction and immense pressure within the accretion disk generates extreme heat, sometimes reaching millions of degrees. At these temperatures, the material emits X-rays, which stream outward from the black hole and into space. One of the most famous examples of a black hole X-ray source is Cygnus X1, a stellar mass black hole about 7,200 light-years from Earth in the constellation Cygnus. Cygnus X1 is locked in a gravitational dance with a nearby star, drawing gas from its companion into an accretion disk. The disk heats up and produces an intense stream of X-rays that astronomers have been observing since the 1960s. In binary systems, where a black hole and a star orbit each other, the intense X-rays can strip material away from the companion star, altering its evolution. Over time, this radiation can erode the outer layers of the star, disrupting its surface and possibly changing its fate. The star may age faster or evolve differently than it would have without the influence of the black hole's radiation, creating a strange, symbiotic relationship where the black hole's presence shapes the life of its neighboring star. For any nearby planets, the intense X-rays from a black hole would be devastating. X-rays are a form of high-energy radiation, and prolonged exposure can strip away planetary atmospheres, especially if the planet orbits close to the black hole. The radiation could also interfere with any chemical processes essential to life. Even if a planet were located at a safer distance, the occasional flares from the black hole's accretion disk could create bursts of radiation strong enough to impact any organisms living on its surface. X-ray emissions from black holes can also be detected over large cosmic distances. Supermassive black holes often produce intense X-rays, which allow astronomers to detect and study them from billions of light-years away. Quasars emit vast amounts of energy across the electromagnetic spectrum, including X-rays. This radiation allows astronomers to detect quasars in distant galaxies, serving as a kind of cosmic lighthouse that illuminates the far reaches of space. X-ray observations of black holes have opened up new ways to study these jets and understand their effects. In many ways, X-ray emissions provide a snapshot of the activity happening near the black hole, capturing the release of energy and its journey through space. This gives scientists a valuable window into the high-energy physics of black holes and the forces that shape galaxies. By studying X-rays, scientists can learn about the size, mass, and even the spin of a black hole. The intensity and variability of the X-ray emissions can reveal details about the black hole's accretion disk, the amount of matter it's consuming, and the behavior of the surrounding gas. In some cases, astronomers can detect quasi-periodic oscillations, or QPOs, in the X-ray emissions, which are thought to be caused by matter orbiting close to the black hole's event horizon. X-ray astronomy has grown tremendously in recent decades, allowing scientists to uncover more about the nature of black holes. Observatories like the Chandra X-ray Observatory and the European Space Agency's XMN Newton telescope have played a crucial role in advancing our understanding of these cosmic phenomena. With the ability to detect X-ray emissions across different wavelengths, these telescopes allow astronomers to explore black holes in greater detail, uncovering mysteries that were once beyond our reach. Despite the dangers associated with X-ray emissions from black holes, these signals are essential for advancing our knowledge of the universe. Without X-rays, many black holes would remain hidden, and we would know far less about their role in cosmic evolution. Supermassive cosmic cannibals, black holes, devouring star clusters. In the heart of many galaxies, black holes go beyond the act of drawing in single stars. They devour entire star clusters. These supermassive black holes, millions or even billions of times the mass of the Sun, can destabilize the regions around them, pulling in not just stars, but dense clusters of them, bound together by their own mutual gravity. This is a wholesale consumption of tightly packed groups of stars, each cluster potentially housing thousands or even millions of suns. When a black hole encounters a star cluster, the stars inside are immediately at risk of being drawn into the black hole's gravitational influence. Because these clusters are usually tightly bound, with stars orbiting close to each other, the disruption of one part of the cluster can lead to a cascading effect. Stars in the cluster move in complex orbits, often interacting with each other as they feel the gravitational force of the black hole. When a cluster is close enough to a supermassive black hole, the gravitational pull on the nearest stars in the cluster becomes so powerful that they begin to spiral inward. As these stars approach the black hole, they can be torn apart by tidal forces, especially if they get too close to the event horizon. This process, known as tidal disruption, occurs when a star is pulled so strongly by the black hole that it stretches, elongating as it spirals closer. Eventually, the star can be shredded entirely, with its gas and material spiraling down into the black hole's accretion disk. This results in a burst of energy, releasing intense X-rays and other forms of radiation, which can be detected from millions of light-years away. The cluster, meanwhile, continues to lose stars, destabilized by the loss of its members and gradually falling apart. Over time, what was once a tight collection of stars might be spread out, leaving only traces of its original structure. The process of devouring star clusters has a ripple effect on the larger galaxy. For instance, the motion of stars near the galactic center becomes influenced by the black hole's gravitational pull, causing more stars to slowly spiral inward. As clusters of stars are consumed or broken apart, the surrounding galaxy can undergo changes. Gas and dust clouds near the black hole get heated and agitated by the radiation released during these tidal disruptions, preventing them from cooling and collapsing to form new stars. The areas near the black hole become regions of star death rather than star birth, and over time, the galactic center may appear depleted of young stars. Observations of many galaxies show evidence of clusters and stars either spiraling into the black hole or having already been absorbed. For example, in the Milky Way, scientists have found stars that seem to be on courses directly influenced by Sagittarius A*. Some of these stars are known as S-stars, a collection of stars orbiting very close to the galactic center. Their high speeds and unusual orbits suggest that many of them were once part of larger groups or clusters, but were scattered due to the gravitational interactions around Sagittarius A*. These stars might represent remnants of clusters that once ventured too close to the black hole, with many of their companions already consumed. Galaxies with larger, more active black holes can have even more dramatic effects on their surroundings. In some galaxies, there are signs that supermassive black holes have devoured multiple clusters, leaving evidence in the form of high-energy jets and X-rays. Over billions of years, black holes that continue to feed on clusters can grow to monstrous sizes, especially if the clusters contain dense groups of stars that are readily available. By devouring clusters, they are able to grow at a rate faster than by simply consuming individual stars. This means that a galaxy with many dense star clusters could, in theory, have a central black hole that grows faster and becomes more massive than those in galaxies with fewer clusters available for consumption. As the black hole grows and absorbs more material, it continues to exert a stronger gravitational influence, further destabilizing the region around it. Star clusters, especially those that stray into its reach, find it nearly impossible to remain intact. The process accelerates as more stars are drawn into the black hole's pull. Each cluster represents a rich source of mass for the black hole, allowing it to expand and exert even more control over its surroundings. When a cluster is absorbed, the material that spirals into the black hole releases more energy than the entire Milky Way generates in a year. This energy can radiate outward, creating powerful jets that blast through the galaxy. These jets, composed of high-energy particles, can travel for hundreds of thousands of light years, piercing through the galaxy's layers and even affecting neighboring galaxies. In some cases, they collide with nearby gas clouds, compressing them and possibly triggering bursts of star formation far from the black hole's location. Black hole stars. Theories on stars made of pure black hole matter. In the speculative reaches of astrophysics, there exist these hypothetical objects that are among the strangest concepts that scientists have proposed. Black hole stars. Black hole stars, if they exist, would be objects so massive and dense that they verge on becoming black holes themselves, or perhaps house a black hole at their core. They represent a fusion of two of the universe's most powerful and mysterious forces: the life of stars and the profound gravitational pull of black holes. Stars shine by converting hydrogen into helium through nuclear fusion, a process that produces the energy and light we see. This fusion process generates immense pressure that counteracts the force of gravity, keeping the star from collapsing under its own weight. In large stars, this fusion continues with heavier and heavier elements until it reaches iron, after which fusion no longer provides energy. For the most massive stars, this signals the end of their stable lives, leading to a collapse and often a violent explosion called a supernova. If the remnants of the collapsed star are dense enough, they form a black hole. One theory, however, suggests that in the early universe, before galaxies and typical stars formed, there may have existed stars so massive that they behaved differently from anything seen today. These primordial black hole stars would have been hundreds of times larger than the largest stars we know of, containing enough mass to prevent them from collapsing immediately under their own gravity. Instead of collapsing directly into a black hole, these stars could have sustained themselves for a time, existing in a quasi-stable state where their intense gravity balanced against some form of pressure, possibly radiation, or the mysterious effects associated with black hole formation. One of the ideas behind black hole stars is that they could form a kind of shell around a black hole, with the black hole itself residing at the core. In this scenario, the black hole does not instantly consume the entire star, but rather feeds on it gradually from within. As the black hole at the center pulls in material, it would generate incredible amounts of energy, potentially creating intense radiation pressure that pushes outward and stabilizes the outer layers of the star. This push-pull dynamic could, theoretically, allow the outer parts of the star to exist for a time, even as the core continues to collapse into the black hole. This balance would delay the total collapse, enabling the star to exist in a unique, almost liminal state between a star and a black hole. Another idea is that in some cases, black hole stars might form without a black hole at their core, instead reaching a state where they are on the edge of collapse, but held in check by their own massive energy output. These stars would be nearly incomprehensible in size and brightness, their gravity so powerful that they might bend light and distort the space around them. Such stars would essentially be ticking time bombs, teetering on the brink of collapse. Over time, they would lose mass through powerful stellar winds, and once they reached a certain point, they would collapse into black holes. If black hole stars did exist in the early universe, they might have been some of the first objects to collapse and form black holes. They could have served as precursors to the supermassive black holes we find at the centers of galaxies today. Since the early universe was filled with vast clouds of gas and dust, conditions were different from those we see today. Stars could have grown to immense sizes because there were not yet competing forces from other galaxies, stars, or other structures that would limit their growth. These early black hole stars, or at least the black holes they created, might have influenced the formation of galaxies. By injecting energy and gravitational pull into the cosmic fabric, these early giants could have attracted surrounding matter, helping to shape the early galaxies. The gravitational influence of such massive objects would have drawn in gas and dust, perhaps serving as seeds around which galaxies eventually formed. In the unlikely event that a black hole star did still exist somewhere in the universe today, it would be one of the most extreme objects imaginable. Such a star would emit radiation and energy on a colossal scale, with enough gravity to warp space and time around it. The regions near the star's surface would be incredibly hot, possibly glowing with intense radiation. In this way, a black hole star would resemble a small quasar, a powerful energy source fueled by a black hole, but with an entire star's worth of mass still surrounding it. In theory, studying the remnants of these black hole stars, if any still exist or left any traces, could reveal clues about the conditions of the early universe. Observing them, however, would be challenging due to their possible rarity. Some scientists are looking for ways to detect ancient black holes from the early universe, as these might offer indirect evidence that black hole stars once existed. The search involves examining the gravitational effects on surrounding space and the background radiation left over from the Big Bang, looking for any signs that could suggest the presence of such extraordinary objects. White holes, the theoretical mirror, images of black holes. While black holes are regions where everything can fall in but nothing can escape, white holes would be regions where nothing could ever enter, yet matter and energy could emerge out of them. They're like cosmic one-way doors, but with the direction reversed. No information or matter can go in, but information and matter could come out. While black holes trap everything within them once it crosses the event horizon, white holes would have a sort of reverse event horizon, preventing anything from getting too close or entering. But despite the appealing idea of white holes as the cosmic counterparts to black holes, they remain entirely theoretical. No one has ever observed one, and the concept is primarily a solution that comes out of the mathematics of Einstein's theory of general relativity. The idea of white holes arose when scientists looked at the equations describing black holes and began asking questions about symmetry in the universe. According to general relativity, the equations that describe black holes can have a kind of mathematical mirror image that leads to the possibility of a white hole. If a black hole represents a place where space-time curves infinitely inward, a white hole represents space-time curving infinitely outward. In other words, if black holes are cosmic vacuums that draw in everything, white holes would be like cosmic fountains, ejecting matter and energy out into space. While these equations seem valid mathematically, they also create conditions that sound almost impossible to visualize in a physical sense. One idea about white holes is that they could theoretically exist as the endpoints of black holes. This concept comes from the idea of black hole evaporation, or Hawking radiation, which was proposed by Stephen Hawking. In his groundbreaking work, Hawking showed that black holes could emit radiation and, over very long timescales, gradually lose mass and even evaporate completely. Some scientists have speculated that if a black hole eventually loses all its mass, it could transform into a white hole. In this way, a white hole could be the final form of a black hole after it has shed all of its mass and radiation. According to this idea, the information and energy that fell into the black hole might eventually be released as a white hole. This would be a solution to what physicists call the information paradox, the puzzle of what happens to information that enters a black hole. Could a white hole be the universe's way of preserving and releasing that information? Another theory proposes that white holes could be connected to black holes through a sort of cosmic bridge, a tunnel called a wormhole. A wormhole is another hypothetical structure in space-time that has often been featured in science fiction. It's imagined as a shortcut or tunnel between two separate points in space. In the case of black holes and white holes, some physicists have speculated that they might be connected by a wormhole, allowing matter and information to flow from one part of the universe to another through this tunnel. In this model, the black hole would act as the entrance, drawing matter in, while the white hole would act as the exit, spewing that matter out into a different location in space or time. While wormholes are theoretically possible within the framework of general relativity, they would require forms of exotic matter to keep them stable. Exotic matter is a type of hypothetical material with negative energy or negative mass, which hasn't been observed in the universe. This makes wormholes, and by extension any direct link between black holes and white holes, a theoretical concept. White holes, as hypothetical objects, raise a lot of questions. For example, if a white hole can't let anything enter it, what happens to the matter and energy it might release? Would it drift off into the universe in a specific direction? Or would it stay confined near the white hole in some kind of reversed gravitational field? The mathematics of white holes doesn't provide clear answers to these questions. Additionally, the notion of a one-way exit seems to contradict the way gravity works elsewhere in the universe. Since gravity pulls objects together, it seems odd to imagine an object like a white hole that would actively repel anything that got near it. In a universe dominated by forces that pull things together, a structure that pushes everything away feels out of place. Some scientists have suggested that white holes might actually be responsible for some of the unexplained phenomena we observe in the cosmos. For example, the rapid bursts of energy observed in gamma-ray bursts, some of the most powerful explosions we see in the universe, are still not fully understood. A small number of physicists have proposed that these events could be white holes, briefly switching on and releasing a surge of energy before quickly disappearing again. According to this theory, a white hole might form for a fraction of a second, emit a powerful burst of energy, and then collapse or reclose. Some have even wondered if white holes could explain the origin of our universe itself. The Big Bang, which created the universe as we know it, was an event of enormous energy release from a single point. While the Big Bang isn't a white hole in the traditional sense, some scientists have toyed with the idea that it might resemble a white hole in the way it expels matter and energy outward. In this view, what we experience as space expanding could be the effect of a white hole ejecting all matter and energy into existence. Quantum mechanical black holes, exploring the possibility of micro-monsters. When we think of black holes, we picture enormous objects formed by collapsing stars or found at the centers of galaxies. their gravitational pull so intense that they shape whole regions of space. But some scientists believe black holes might exist on a much smaller scale, at the level of particles, where they could be as tiny as atoms. These hypothetical quantum mechanical black holes, or micro-black holes, would form through different processes than their larger counterparts, and though they're invisible to the eye, they might hold secrets that could change our understanding of physics. In quantum mechanics, particles and energy can behave unpredictably, appearing and disappearing or even existing in multiple places at once. Some scientists think that under the right conditions, this unpredictability could lead to the formation of tiny black holes, especially at extremely high energies from intense particle collisions, or perhaps even the extreme conditions of the early universe right after the Big Bang. The Large Hadron Collider, or LHC, the world's most powerful particle accelerator, has been at the center of many discussions about quantum mechanical black holes. When it smashes particles together at near light speeds, it creates a burst of energy that mimics conditions thought to have existed just after the Big Bang. Some scientists hoped that these high-energy collisions might produce tiny black holes, revealing clues about how the universe looked in its first moments. If such black holes did appear, they would be incredibly small, maybe just a fraction of the size of a proton. They would exist only briefly before evaporating, disappearing in a burst of Hawking radiation almost as soon as they formed. For large black holes, this process is incredibly slow, so slow that it would take longer than the current age of the universe for them to evaporate completely. But for a tiny black hole, the process would happen much more quickly. A micro-black hole might only last for a fraction of a second before vanishing in a flash of radiation, taking any trace of its existence with it. One possibility that these tiny black holes might point to is the existence of extra dimensions beyond the three we know. Some theories, like string theory, suggest that there might be hidden dimensions of space that we can't directly observe. These extra dimensions could help explain the existence of micro-black holes, as their formation might depend on the way gravity works in these unseen dimensions. If we ever detect a micro-black hole, it could be a signal that the universe has more dimensions than we currently understand, opening up a new frontier in physics. Quantum mechanical black holes might also help us solve one of the biggest mysteries in science, the unification of gravity and quantum mechanics. Right now, we have two major theories that explain how the universe works. Einstein's theory of general relativity describes gravity and works well for large objects like planets and stars. Quantum mechanics, meanwhile, explains the behavior of particles at the smallest scales. But when we try to combine these two theories, they clash. Black holes might be the key to bridging this gap. A micro-black hole would be a tiny object with incredibly strong gravity, merging the worlds of quantum mechanics and general relativity in a way we've never seen. Studying these quantum black holes could help us find a single, unified theory that explains everything from the largest galaxies to the smallest particles. Some scientists believe that these tiny black holes wouldn't be dangerous to us, as they would evaporate so quickly that they'd barely interact with their surroundings. But others wonder if, under certain conditions, a micro-black hole could stick around for longer than expected. In that case, it might start pulling in particles from its surroundings, growing bit by bit. If one of these black holes somehow grew large enough, it could eventually reach a point where it acted like a traditional black hole, with an event horizon and an inescapable gravitational pull, although the chances of this happening are thought to be very low. In our everyday world, where matter is spread out and particles are tiny, a micro-black hole would struggle to grow, even if it had an extended lifespan. However, this possibility has captured the imagination of scientists and the public alike, sparking imaginations about micro-monsters that could one day roam free from the quantum world. Time, dilation, and the edge of reality. How black holes warp time. In our familiar world, time moves at a constant rate. Seconds tick by with comforting regularity, an even rhythm marking the steady passage of time. Yet near a black hole, this rhythm becomes warped and twisted. The intense gravity of these cosmic giants has the power to stretch and slow time itself, creating a surreal experience for anything or anyone approaching the black hole. This strange effect is called time dilation, a consequence of Albert Einstein's theory of relativity, which tells us that time doesn't flow at the same rate everywhere. It can be altered by both gravity and speed. As an object approaches a black hole, it begins to feel the effects of time dilation. Let's imagine an astronaut on a journey toward a black hole, while a second astronaut watches from a safe distance, far enough away that they don't feel the black hole's gravity as intensely. As the first astronaut moves closer to the black hole, the strong gravitational field begins to slow down time relative to the distant observer. To the second astronaut watching from a distance, it would seem as if the first astronaut were moving in slow motion. Every movement, every gesture would appear stretched out, almost frozen. But for the astronaut moving toward the black hole, time would feel completely normal. They would experience no change in their perception of time passing. They'd still think and move at their usual pace, unaware of the slow motion effect seen by the observer. This phenomenon grows more extreme the closer the astronaut gets to the event horizon. At this edge, the time dilation effect becomes so powerful that to an outside observer, it would appear as if the astronaut were almost completely frozen in time, suspended just above the event horizon. Minutes would pass, then hours, then years, and still, the astronaut would seem trapped in that moment, barely moving, as though caught in a sort of three-dimensional holographic photograph. For the astronaut approaching the black hole, this experience is very different. They would continue moving forward, crossing the event horizon without realizing they appeared frozen to any distant observers. If they looked back at the universe behind them, they'd see something equally strange. All of the light from the stars, galaxies, and even the distant planets would appear to be speeding up, as if the rest of the universe were racing forward in time. This is the effect of gravitational time dilation in reverse. While those far from the black hole see the astronaut slowing down, the astronaut experiences the universe speeding up. Everything outside the black hole's influence would seem to accelerate, racing through epochs, with stars appearing to age and die in mere moments. This time dilation effect near a black hole can be so extreme that theoretically, an observer falling into a massive enough black hole might watch the entire future of the universe unfold in a matter of seconds, seeing the rise and fall of galaxies, the birth and death of stars, and perhaps even the end of time itself. This eerie experience at the event horizon represents a point where the laws of physics as we know them start to break down, where space and time blur into something unrecognizable. The astronaut's fate past the event horizon remains a mystery, hidden from view by the very nature of the black hole itself. Another part of this effect is the way black holes curve space itself. In everyday life, we live in what seems like a flat, three-dimensional world, where the shortest distance between 2 points is a straight line. But near a black hole, space becomes curved to the point where that straight line warps and twists. If we imagine space as a flat rubber sheet, a black hole would be like a heavy weight pressing down on the sheet, creating a deep, funnel-like indentation. Anything moving close to this indentation would be pulled toward it, forced to follow the curved paths created by the gravity of the black hole. For an object moving through this curved space, the experience is unsettlingly strange. It wouldn't feel as if it were being pulled along a curved path, but rather that the very fabric of space itself was bending beneath it, drawing it closer to the black hole's core. Even light, which usually travels in straight lines, is forced to bend and warp in the presence of this immense gravity. This is why black holes appear so dark. Light can't escape the event horizon, and any light emitted from an object near the black hole is either pulled inward or stretched to the point of invisibility. The closer light gets to the black hole, the more it loses its energy, becoming redder and fainter. To a distant observer, This creates a phenomenon called gravitational redshift. Light coming from the astronaut falling into the black hole would appear increasingly red and dim as they neared the event horizon, until it faded from view altogether, leaving the astronaut's image to disappear into the darkness. The edge of a black hole's event horizon isn't just a physical boundary, it's a boundary in our understanding. The way black holes manipulate time and space, seemingly defying the usual rules, hints at a hidden layer of physics that we have yet to uncover. Some scientists believe that studying black holes could eventually lead us to a theory of everything, a single framework that explains both the smallest particles and the largest cosmic structures. Spaghettification, the gruesome fate of objects near a black hole. Spaghettification is the stretching and elongating of an object as it approaches a black hole's event horizon. Anything that gets close enough, whether it's a star, a planet, or a person, will face this fate if it drifts too far into the gravitational grip of a black hole. On our planet, gravity pulls everything downwards, keeping us grounded to the surface. But this force is relatively weak compared to what happens near a black hole. The closer you get to a black hole, the more intense the gravitational pull becomes. And because black holes are so incredibly dense, with all their mass concentrated in a tiny space, their gravitational field intensifies at a rate that far exceeds anything we experience on Earth. For an object approaching a black hole, the difference in gravitational pull from one end of the object to the other becomes enormous. Imagine an astronaut drifting toward a black hole feet first. The gravitational force pulling on the astronaut's feet would be significantly stronger than the force pulling on their head, simply because their feet are closer to the black hole. This difference in force is known as a tidal force. With the feet being pulled far more intensely than the head, the astronaut's body would start to stretch, elongating like a piece of spaghetti. The closer they get to the black hole, the stronger this effect becomes, until the entire body is stretched into a thin, elongated shape. As the tidal forces increase, the spaghettification process doesn't just stretch the object, it also compresses it horizontally, making it narrower and narrower while it gets longer and longer. Essentially, the object becomes a thin line, pulled toward the black hole in an almost stream-like fashion. Eventually, these forces become so extreme that they can overcome the atomic bonds holding the object together. At this point, the astronaut or any object would be torn apart completely, disintegrated into atoms that continue their descent toward the event horizon. For a human observer, this process would be unimaginably painful and frightening. But interestingly, the victim wouldn't necessarily be able to feel the spaghettification at first, especially if they were falling into a massive black hole. Larger black holes have event horizons far from their central singularities, meaning that the tidal forces near the event horizon aren't quite as extreme. This would allow the person to cross the event horizon without immediate disintegration. It's only as they move closer to the singularity, the point at the very center of the black hole, where the tidal forces reach their peak, pulling the object apart atom by atom. In smaller black holes, however, the story is different. These black holes have more intense tidal forces closer to their event horizons, meaning that any object nearing this boundary would begin experiencing spaghettification well before crossing into the black hole. In these cases, spaghettification becomes unavoidable right outside the event horizon. Anything that gets too close is rapidly pulled into the elongated shape and disintegrated before even reaching the point of no return. It's not just hypothetical astronauts who would experience this fate. Stars that wander too close to a black hole can also be pulled apart and stretched by these same tidal forces. When a star falls under the influence of a black hole, the star's outer layers are stretched and pulled away, forming long, twisting streams of hot gas that spiral into the black hole. As these stellar remnants move inward, they heat up to millions of degrees, creating brilliant flares of X-ray radiation that can be observed from Earth. This phenomenon known as a tidal disruption event, gives astronomers a rare opportunity to witness spaghettification on a massive scale. Observing these events helps scientists estimate the black hole's mass. By studying how a star is pulled apart and the rate at which its gas spirals inward, astronomers can determine just how much gravitational force the black hole is exerting, which in turn tells them more about the black hole's size and influence. The Great Attractor, a supercluster pulling black hole mystery. The Great Attractor is a gravitational enigma located in a region of space hidden behind the thick clouds of dust and stars of our own Milky Way, making it difficult to observe directly. Yet, even without a clear view of what's there, astronomers know that something incredibly massive and powerful is pulling galaxies towards it, including our own galaxy. The force exerted by this unseen presence, known as the Great Attractor, is so immense that it's influencing the movements of entire galactic clusters across millions of light years. In the vast emptiness of the universe, where galaxies often drift apart, it's remarkable to find such a powerful center of attraction that defies the norm. Most galaxies are expected to follow a pattern of recession, moving away from each other due to the expansion of the universe. But in the area surrounding the Great Attractor, galaxies aren't moving away. Instead, they seem to be converging towards a central point. This convergence suggests the presence of a gravitational force strong enough to overcome the natural expansion of the universe in that region, creating a strange cosmic imbalance. Astronomers initially estimated that this gravitational anomaly was located around 200 million light-years away in the direction of the constellation Centaurus. However, pinpointing the exact nature of the Great Attractor has proven challenging. Because it sits in a region of space known as the zone of avoidance, our view is blocked by the gas, dust, and stars within the plane of the Milky Way. Radio telescopes and X-ray observatories have allowed scientists to peer through this barrier to some extent, but the data remains incomplete. One of the prevailing theories is that the Great Attractor is associated with a supercluster of galaxies, a vast structure made up of many smaller galaxy groups bound together by gravity. Specifically, some researchers believe that the Great Attractor may be part of the larger Laniakea supercluster, which includes the Virgo cluster, to which the Milky Way belongs. However, this only raises further questions, as superclusters themselves are massive, but usually spread out, with enough empty space between galaxies to prevent such intense gravitational influence in any one area. For the Great Attractor to be pulling galaxies inward so strongly, something extremely dense and massive must be at its core. This is where the possibility of black holes comes into play. Astronomers have considered that the Great Attractor might harbor a collection of supermassive black holes, each capable of exerting powerful gravitational influence. If this were the case, these black holes would not be isolated, but rather packed together within the core of a vast galactic cluster. Such an assembly could explain the intensity of the gravitational pull, as the combined masses of multiple black holes would generate a force unlike anything we typically observe on this scale. However, for black holes alone to account for this level of attraction, they would need to be extraordinarily massive or gathered in an unusually high concentration, unlike anything observed in more familiar parts of the universe. Some researchers propose that the Great Attractor could be a dense concentration of dark matter, which could explain why we can't see it and why it exerts such a powerful influence on surrounding galaxies. Interaction between dark matter and black holes in this area may amplify the gravitational force, creating the pull we observe. If a large amount of dark matter is clustered in this hidden region, it could be influencing the movement of galaxies without us ever seeing what's actually there. Researchers have identified another anomaly called the Shapley supercluster, located even farther away, which appears to be pulling galaxies in a similar way. This suggests that there might be a chain of massive structures, with one region of gravitational pull giving way to an even larger one in a kind of cosmic relay, where matter is drawn from one massive structure to the next. If black holes do contribute to the Great Attractor's mass, they might represent the endpoints of countless galaxies and star clusters that have been consumed over billions of years. Supermassive or ultramassive black holes could merge into even bigger black holes, contributing to the gravitational mass and slowly building up over time. This would mean that the great attractor isn't a static object, but an evolving structure that grows as more material is drawn in. Sagittarius A*, the supermassive black hole at our galaxy's heart. At the center of the Milky Way lies a cosmic giant, the supermassive black hole Sagittarius A*. This object, nestled within the galactic core about 26,000 light-years away from Earth, remains largely invisible to the naked eye, hidden by clouds of gas and dust that shroud the galactic center. Roughly 4 million times the mass of our Sun, Sagittarius A* is a behemoth of gravitational influence. This massive black hole holds sway over the central regions of the Milky Way, affecting the orbits of nearby stars and influencing the distribution of gas and dust within our galaxy's inner core. Its gravitational pull helps stabilize the region, giving the galaxy its characteristic spiral shape. Without it, the core of the Milky Way might be far more chaotic, with stars and gas clouds flying off in unpredictable directions. In many galaxies, supermassive black holes at their centers are voracious eaters, feeding on gas, dust, and any star that strays too close. However, Sagittarius A* doesn't emit this kind of intense energy. Astronomers consider it to be in a dormant or inactive state, meaning it isn't actively feeding on surrounding material at the same rate as other supermassive black holes. While it does occasionally flare up with bright flashes of X-ray or infrared light, these episodes are brief and much less dramatic than what we observe from black holes in more active galaxies. One theory suggests that there simply isn't much material left around it to feed on. Over time, Sagittarius A* may have consumed or ejected much of the nearby gas and dust, leaving it with a sparse environment in which to operate. Without a consistent supply of fuel, the black hole doesn't have the chance to release the intense radiation that we see from more active galactic cores. Occasionally, however, a passing cloud of gas or a star that drifts too close might be pulled in, causing a brief period of activity. In these rare cases, astronomers have observed Sagittarius A* brighten temporarily before fading back into quietude. Even though Sagittarius A* is mostly inactive, the stars that orbit close to it provide vital clues about its nature. One of the most famous observations involves a star known as S2, which follows an elongated orbit around Sagittarius A* and comes extremely close to the black hole at one point in its path. Studying S2's movement has allowed scientists to map out the gravitational field of Sagittarius A* in detail. When S2 reaches the closest point of its orbit, or pericenter, it experiences the intense pull of the black hole, accelerating up to 25 million kilometers per hour. Magnetic fields are common in space, but around black holes, they can twist and contort in unusual ways. Astronomers have noticed that the magnetic field near Sagittarius A* appears to change direction frequently, which may be linked to the movement of hot gas and the black hole's spin. The environment around Sagittarius A* is also home to dense clouds of gas and other intriguing features. One example is a mysterious structure called the Fermi bubbles. These are enormous bubbles of high-energy particles that extend above and below the plane of the Milky Way, reaching far beyond the galaxy's disk. Some scientists believe these bubbles might be linked to past activity of Sagittarius A*, possibly from a period when it was more active and expelled jets of material into space. If this theory is correct, then the Fermi bubbles serve as a sort of fossilized record, preserving evidence of a time when Sagittarius A* might have been more like the active black holes we see in other galaxies today. Though Sagittarius A* is currently calm, it's possible that it could become active again if a sufficient amount of material finds its way to the galactic center. Whether it's a massive gas cloud or a cluster of stars that strays too close, An encounter with Sagittarius A** could trigger a dramatic feeding event, temporarily lighting up the core of the Milky Way with bursts of energy. For now, however, it remains a mostly silent giant, holding the galaxy together in its gravitational embrace. The peculiar case of GRS 1915 plus 105, the largest stellar black hole in our galaxy. Among the stellar black holes known in our galaxy, GRS 1915 plus 105 stands out as one of the most massive stellar black holes in the Milky Way, with a mass estimated to be between 10 and 14 times that of our Sun. Located about 28,000 light-years from Earth in the constellation Aquila, GRS 1915 plus 105, or V1487 Aquila as it's also called, is not just notable for its size, it's remarkable for its unpredictable behavior and violent activity. This black hole, which is part of a binary system, has intrigued astronomers for years because of its unusual outbursts and fluctuations. Unlike many black holes that experience periods of calm punctuated by occasional bursts of activity, V1487 Aquila seems to be constantly teetering on the edge of a cosmic tantrum. Its emissions are erratic and powerful, producing X-ray outbursts that can be thousands of times brighter than our Sun. These emissions are not only intense, but are also incredibly varied. Sometimes they flare up in a matter of seconds, while at other times, the outbursts last for minutes or even hours. This volatility has earned V1487 Aquila a reputation as one of the most unpredictable black holes ever studied. The source of this activity lies in the black hole's feeding habits, which are unlike those of most other black holes. V1487 Aquila has a companion star from which it draws matter, siphoning gas away through gravitational forces. In many black holes, the accretion disk is relatively stable, allowing material to gradually flow into the black hole. But in the case of V1487 Aquila, this disk is highly unstable. The material in the disk accumulates and then releases in powerful bursts, leading to the frequent and erratic flares. Astronomers believe that these irregular bursts are due to a process known as the Eddington limit, which is a balance between the gravitational pull of the black hole and the outward pressure created by intense radiation. When too much material builds up in the accretion disk, the pressure from radiation pushes back against the gravitational pull, temporarily halting the inflow of matter. This causes the material to pile up, only to crash inward in a powerful wave when the pressure eases. This back-and-forth process creates a cyclical pattern of buildup and release, resulting in the explosive X-ray outbursts that make the black hole so unique. The energetic outbursts from V1487 also create spectacular jets of matter that shoot out from the black hole's poles. These jets, known as relativistic jets, travel at nearly the speed of light and extend out thousands of kilometers into space. Scientists believe that the intense magnetic fields around the accretion disk are responsible for launching these particles at such high speeds, ejecting them into space in narrow beams. Much like its X-ray emissions, the jets are highly erratic, flickering on and off and changing in intensity. In fact, astronomers have classified V1487 Aquila's activity into several different modes, each representing a different combination of disk behavior, X-ray emission, and jet production. Some modes produce powerful, steady jets, while others generate weaker, sporadic ones. Black holes can spin at various speeds, depending on how much angular momentum they have acquired over their lifetimes. For V1487, the spin is exceptionally high, close to the maximum possible rate for a black hole. This rapid rotation affects everything around it, from the shape of the event horizon to the dynamics of the accretion disk. In particular, the high spin rate likely enhances the power of the jets, allowing them to reach relativistic speeds. Cygnus X1, the first confirmed stellar black hole and its astounding power. In the world of black hole research, Cygnus X1 holds a special place. It was the first stellar black hole ever confirmed, and its discovery marked a milestone in our understanding of these objects. Cygnus X1 is a powerful source of X-ray emissions located in the constellation Cygnus, about 7,300 light-years from Earth. This black hole belongs to a binary system, locked in a gravitational dance with a large companion star. In the early 1960s, scientists detected intense X-ray emissions coming from a seemingly empty spot in the sky. These emissions puzzled astronomers. At the time, X-rays from outer space were still new territory, and the sources of such powerful emissions were not well understood. As scientists observed this object more closely, they realized that it was emitting X-rays at a level far beyond what ordinary stars could produce. Eventually, the source of these X-rays was traced back to a binary system, where a massive star, now known as HDE 226868, appeared to be orbiting an invisible but extremely massive companion. This companion was Cygnus X1, and it wasn't long before astronomers realized they were looking at something unlike anything ever observed. Cygnus X1's story was propelled forward when Stephen Hawking famously bet the future Nobel Prize-winning physicist Kip Thorne in the 1970s that Cygnus X1 was not a black hole. At that time, the idea of black holes was still theoretical, and many scientists were hesitant to accept the existence of such extreme objects. However, as more data came in, it became clear that Cygnus X1 met all the criteria for a black hole, a dense, invisible object with a gravitational pull strong enough to prevent even light from escaping. In 1990, after years of accumulating evidence, Hawking conceded the bet, and Cygnus X1 was confirmed as a black hole. One of the defining features of Cygnus X1 is its intense and steady X-ray output. Cygnus X1's companion star, HDE 226868, is a massive blue supergiant, and it is losing material due to the gravitational influence of the black hole. Cygnus X1 pulls in a stream of gas from this star, forming a high-energy accretion disk. The material in this disk is compressed and heated to millions of degrees, creating a powerful X-ray glow. In fact, the X-ray emissions from Cygnus X1 are one of the strongest X-ray sources detectable from Earth. The inner regions of the accretion disk, where temperatures and densities are highest, emit the most intense X-rays, creating a spectacle that can be observed across vast distances. Astronomers have determined that Cygnus X1 is rotating at an exceptionally high rate, close to 790 times per second. The high spin rate also suggests that Cygnus X1 may have experienced a unique formation process. One possibility is that it formed from the collapse of a very massive star that imparted its angular momentum to the black hole. Alternatively, Cygnus X1 could have gained additional spin by accreting material from its companion over time. Since Cygnus X1's companion star is still relatively young, it offers a rare opportunity to observe a black hole in the early stages of its life in a binary system. Over time, the companion star will continue to lose mass, eventually evolving into a different type of star, or possibly exploding as a supernova. The discovery of M87*, a glimpse into a supermassive monster beyond our galaxy. In April 2019, the world saw the first ever image of a black hole. That black hole was M87*, a supermassive giant sitting at the center of one of the largest known galaxies, Messier 87, some 53 million light-years away. The blurred but iconic image captured by the Event Horizon Telescope, or EHT, was a historic achievement, marking the first time humanity visually confirmed the presence of a black hole's event horizon. M87*, a black hole with a mass of between 3 to 6 billion times that of the Sun, was now within our reach, at least in terms of observation. The galaxy M87 itself is one of the most massive galaxies in the nearby universe, located in the Virgo cluster, a collection of galaxies bound together by gravity. M87 is filled with stars, gas, and dust, and at its heart lies M87*. It's a black hole of a scale we rarely see, a true supermassive black hole whose influence stretches far across its galaxy. The black hole's mass is so enormous that it alters the orbits of stars millions of times farther out, essentially controlling the gravitational structure of the entire galaxy. The Event Horizon Telescope is not a single telescope, but rather a global network of radio telescopes spread across the planet. These telescopes, located at sites like Hawaii, Mexico, Antarctica, and Spain, combine their observations through a technique known as Very Long Baseline Interferometry, or VLBI. By linking up telescopes across Earth, scientists effectively created a planet-sized telescope capable of capturing details at an unprecedented level of precision. Each telescope in the network collects radio waves emitted by M87*, gathering data across vast distances to build a detailed picture. The black hole's incredible distance from Earth would make it seem nearly impossible to observe in such detail, but VLBI allowed scientists to achieve the necessary resolution. This process required algorithms that could fill in gaps in data, essentially reconstructing the final image from incomplete signals. The resulting image of M87** wasn't sharp in the way we might expect from a photograph. Instead, it was a hazy, glowing ring encircling a dark core. This dark center is the shadow of the black hole, the spot where gravity is so strong that even light cannot escape. The glowing ring is created by gas and dust heated to extreme temperatures as they swirl around the black hole, close to the event horizon. It's here, on this edge, that light is bent by gravitational forces so intense that it creates a ring-like appearance. General relativity predicted the shape and structure of the event horizon's shadow, and the actual image of M87** aligned remarkably well with these predictions. The dark center, surrounded by the ring of light, fit the theoretical models almost precisely. For physicists, this was a significant moment, an observational confirmation that general relativity still held up, even in the most extreme environments we can imagine. M87** is a particularly active black hole, meaning it feeds on a steady supply of matter drawn from its surroundings. The swirling gas and dust around M87** emit massive amounts of energy, and some of this material is funneled into jets that shoot out from the poles of the black hole. The jets from M87** are among the most powerful known, capable of shaping the surrounding galaxy by blasting material outward, influencing star formation, and altering the distribution of gas within M87 itself. The material around M87** doesn't just spin in random directions. It forms an accretion disk that is closely aligned with the direction of the jets. By studying these jets and their orientation, astronomers can determine the black hole's rotation and gain insights into how M87** interacts with the galaxy. The fact that M87** produces jets at all suggests it's a rapidly spinning black hole, as the rotation of the black hole's magnetic field likely plays a role in driving the jets. The EHT project involved hundreds of scientists, engineers, and institutions from around the world, each contributing expertise, resources, and time. It took years to coordinate the telescopes, process the data, and reconstruct the image. In fact, the amount of data collected by the EHT was so vast that it couldn't be transmitted digitally. Instead, hard drives were flown across the world to be analyzed. A black hole consuming its own galaxy, the tail of NGC 4889. In the distant Coma cluster lies a massive elliptical galaxy named NGC 4889, home to one of the largest black holes known to astronomers. This supermassive black hole, hidden within the center of NGC 4889, has a mass estimated to be around 21 billion times that of the Sun, about 3 to 6 times larger than the humongous M87*. That's about 5,200 times the mass of the black hole at the center of our own Milky Way. NGC 4889 is a giant elliptical galaxy, meaning it doesn't have the spiral arms or disc-shaped structure seen in galaxies like the Milky Way. Instead, It appears as a smooth, rounded mass of stars and interstellar material. The presence of this colossal black hole has likely contributed to this shape, as well as to the sparse and relatively uniform distribution of stars throughout the galaxy. Massive black holes, especially those of this size, often play a major role in determining the form of their host galaxies, and NGC 4889's black hole is no exception. At the heart of NGC 4889, the black hole has an enormous gravitational sphere of influence. Stars that pass close to this central region have their orbits altered or even disrupted entirely. For any material that ventures too close, there's a point of no return. Once it crosses the event horizon, it's pulled inward with no chance of escape. As a result, the core of NGC 4889 is a dynamic and intense place, where the central black hole exerts constant pressure on its surroundings. Over time, this relentless gravitational force has stripped the central regions of NGC 4889 of much of their star-forming gas. Gas clouds that drift near the black hole can be trapped by its pull, where they become part of an accretion disk. As the gas compresses and heats up, it releases an enormous amount of energy, often in the form of powerful jets that shoot out from the galaxy's center. Normally, a galaxy's star formation is fueled by cool gas, which condenses into dense clouds where new stars are born. But in NGC 4889, the central black hole has heated and expelled much of this gas, disrupting the conditions necessary for star formation. The powerful jets and radiation emitted by the black hole's accretion disk have driven gas away from the galaxy's core, creating an environment where new stars struggle to form. The galaxy's current population of stars is likely very old, having formed billions of years ago when conditions were different. Since then, the galaxy has become a place of relative quiet, with little new star formation to replenish its aging stellar population. During an earlier era, likely several billion years ago, this black hole could have been a quasar. Quasars are among the brightest objects in the universe, and if NGC 4889's black hole was once a quasar, it would have emitted such powerful radiation that it would have shaped not only the structure of its own galaxy, but also potentially impacted nearby galaxies in the Coma cluster. Over time, however, the black hole's activity may have slowed as it exhausted the available gas supply, settling into a quieter phase where it no longer shines as brightly. Without enough cool gas to fuel new star formation, NGC 4889 has evolved into a galaxy where old stars dominate, forming a stable but inactive stellar population. In this way, the black hole's hunger for material has shaped the very nature of the galaxy, creating a sort of cosmic desert where new stars rarely emerge. One intriguing question that astronomers are still investigating is whether NGC 4889's black hole is still growing. Although it's no longer as active as it might have been during its quasar phase, there's a possibility that the black hole continues to draw in small amounts of gas and other material. As it does, it may release occasional bursts of energy. These sporadic emissions could reveal clues about the black hole's current state, providing a glimpse into the mechanisms that drive its activity. Quantum entanglement at the event horizon, a new frontier of study. Quantum entanglement is a fascinating property in quantum mechanics, where two particles become so deeply connected that the state of one instantly affects the state of the other, no matter how far apart they are. This connection is so immediate that it appears to happen faster than the speed of light, something Einstein famously called spooky action at a distance. Entanglement is one of the core principles of quantum mechanics. When applied to black holes, entanglement presents both exciting possibilities and challenges, particularly when it comes to what happens to information near the event horizon. One of the great puzzles in black hole physics is what happens to information that falls into a black hole. In the world of quantum mechanics, information about particles, such as their spin, charge, and other properties, can't simply disappear. But according to general relativity, anything that crosses the event horizon should vanish, consumed by the black hole, and lost forever. This apparent contradiction between quantum mechanics and relativity has led to what's known as the information paradox. Many physicists believe that understanding quantum entanglement around the event horizon might provide clues to resolving this paradox. One idea is that particles that approach the event horizon become entangled with particles on the other side, creating a sort of quantum bridge between the inside and outside of the black hole. This entanglement could, in theory, preserve information even if it crosses the event horizon. In this scenario, the event horizon would act almost like a hologram, storing a faint shadow of all the information that has ever fallen into the black hole. A much-debated theory known as the firewall paradox emerged in recent years, challenging the conventional view of black holes as smooth, calm boundaries in space. According to this paradox, if information is truly preserved at the event horizon through entanglement, it could lead to a buildup of energy at this boundary. This energy, in turn, might create a firewall, a searing wall of radiation that would destroy anything approaching the event horizon. For decades, scientists believed that an object would be able to cross the event horizon without any dramatic change in its experience, following the logic of general relativity. The firewall paradox, however, proposes a scenario where, instead of falling smoothly into a black hole, anything that approaches the event horizon would be obliterated by intense radiation. This idea has sparked intense debate among physicists, with some arguing that such a barrier conflicts with other well-established principles of physics. If firewalls exist, they would violate what is known as the equivalence principle, a cornerstone of Einstein's theory of general relativity, which states that free-falling observers should not experience any strange effects at the event horizon. Yet, if firewalls do not exist, then how does quantum information escape, being destroyed inside the black hole? Research in quantum mechanics suggests that entanglement at the event horizon could allow for a form of information leakage, where the properties of particles that fall into the black hole remain entangled with particles outside it. This idea leans on what physicists call monogamy of entanglement, which states that particles cannot be maximally entangled with more than one other particle at the same time. When applied to black holes, this concept implies that if a particle outside the event horizon is entangled with a particle that has fallen in, this connection might break previous entanglements, releasing information in a subtle and indirect way. Through this mechanism, the information that enters a black hole might not be entirely lost, but could instead slowly radiate back into the universe, spread out over time through particles that escape the black hole's pull. Physicists are exploring how to test these theories, using the tools of quantum mechanics and general relativity, but the extreme environments near black holes make direct observation difficult. Despite these challenges, advances in quantum physics are helping researchers develop theoretical frameworks to understand entanglement at the event horizon. Experiments in quantum information science, such as those that manipulate entangled particles in the lab, are providing insights that scientists hope to apply to the study of black holes. By understanding how entanglement works in controlled settings, they aim to gain a better understanding of how entanglement might behave under the intense gravitational forces around black holes. Some physicists speculate that entangled particles on opposite sides of a black hole's event horizon could create a type of microscopic wormhole, linking distant points in space-time. This idea, known as ER=EPR, combines concepts from Einstein and physicist Nathan Rosen's work on wormholes, aka ER, with Einstein, Podolsky, and Rosen's work on quantum entanglement, aka EPR. While this theory is highly speculative, it opens up the possibility that entanglement might play a role in shaping the structure of space-time itself, especially in the regions surrounding black holes. The phenomenon is incredibly complex, involving calculations that stretch the limits of our most advanced physics models. Some scientists speculate that fully understanding entanglement around black holes could require a new form of mathematics, or even a new approach to physics altogether. The mathematical tools we currently have were developed to describe worlds that follow consistent rules and predictable patterns, but black holes defy many of these conventions. The singularity problem. Do black holes really have infinite density? The common understanding, based on Einstein's theory of general relativity, suggests that a singularity forms a place of infinite density, where all the matter that has fallen into the black hole is squeezed into a point of zero volume. At first glance, this might sound straightforward. Gravity crushes everything down to an unimaginable degree, creating a place where mass and density spike to values that reach infinity. But infinite density is a concept that doesn't quite fit with how we understand physics. It leaves us with a challenging puzzle. Is it possible that black holes really have infinite density? Or is something else happening deep within? In a conventional sense, physics deals with measurable quantities and defined limits, and infinity isn't a number or value that physicists work with comfortably. When we speak about the infinite density at the singularity, it's often more a reflection of the limitations of our current theories than of what's actually there. The mathematics of general relativity breaks down when it tries to describe what's happening inside a black hole. It can't handle the intense gravitational field or the compression of matter beyond a certain point. So instead of providing a clear answer, the equations of relativity leave us with this notion of an infinitely small, infinitely dense point at the core of a black hole, which is known as the singularity. The concept of a singularity has always been a thorny issue for physicists, largely because it highlights a conflict between general relativity and quantum mechanics. When you try to apply both theories to the singularity, they clash. General relativity insists that gravity is so strong at the singularity that it warps space-time infinitely. But quantum mechanics, which describes matter at tiny scales, suggests that there should be some sort of limit to how much matter can be compressed. These two theories refuse to reconcile with each other when faced with the singularity, which has led physicists to search for a more complete theory of quantum gravity, something that can describe both the massive gravitational forces of black holes and the tiny quantum particles that fall into them. Several ideas have been proposed to address this singularity problem, with the goal of explaining what happens inside black holes without resorting to infinity. One of the leading concepts is string theory, which suggests that the basic building blocks of the universe aren't particles, like electrons or quarks, but rather tiny, vibrating strings of energy. These strings can take on different forms and interact with one another in ways that could potentially smooth out the singularity, avoiding infinite density, and creating a finite, if incredibly small, core within the black hole. Another approach is called loop quantum gravity, according to which space is not a continuous fabric, but is instead made up of tiny, discrete units or loops. This theory suggests that there's a fundamental graininess to space at the smallest scales, and this could provide a natural limit to the density that matter can reach inside a black hole. In this view, rather than collapsing into an infinitely small point, the matter inside a black hole might form a highly compact but finite structure, where space is bent but not torn into infinity. There's also the idea that, rather than having an actual point of infinite density, the singularity could be a phenomenon related to the event horizon itself. Some physicists propose that, from the perspective of an outside observer, the matter that falls toward a black hole never actually reaches the singularity. Due to the effects of extreme time dilation near the event horizon, it appears as though the infalling matter slows down more and more, freezing just above the event horizon as time stretches toward infinity. In this interpretation, the singularity isn't so much a place inside the black hole, as it is a consequence of the distortion of space-time around it. Quantum mechanics offers some hints about what might be happening at the singularity, particularly with concepts like the uncertainty principle. This principle suggests that there's a fundamental limit to how precisely we can know certain properties, like a particle's position and momentum at the same time. In the intensely compressed environment of a black hole, this uncertainty could create a situation where particles maintain a certain quantum fuzziness, which would prevent them from being crushed into a single point. This kind of quantum pressure might counteract the pull of gravity, creating a sort of quantum core instead of a true singularity with infinite density. Stephen Hawking and others have contributed additional ideas to the mystery of the singularity. Hawking proposed that black holes aren't completely black, but instead emit Hawking radiation, a faint glow of particles that gradually reduces the black hole's mass over time. If black holes can slowly evaporate and lose mass, it raises questions about what would happen to the singularity as the black hole shrinks. Some theories suggest that, as the black hole loses mass, the intense gravitational forces would decrease, possibly revealing a finite structure at the center rather than a singularity. In this scenario, the black hole might eventually evaporate entirely, leaving behind only a tiny remnant, but one that doesn't have infinite density. Some propose that instead of crushing matter down to a point of infinite density, the intense gravitational forces inside a black hole might create a passage to another universe or a new region of space. This idea, often called a white hole, suggests that black holes could act as portals, with matter entering through the black hole and emerging somewhere else. Holographic black holes, a new theory that changes everything we know. The holographic black hole idea posits, what if black holes could store information in a way that resembles a hologram? This idea doesn't refer to holograms like the ones used in entertainment, but rather a mathematical description in which three-dimensional information is represented on a two-dimensional surface. The theory suggests that a black hole's event horizon might contain everything we need to know about what's inside, much like how a hologram on a credit card contains information about a three-dimensional image on its flat surface. One possible solution to the information paradox of black holes came from the development of the holographic principle, introduced by physicists Gerard Hooft and Leonard Susskind. They suggested that perhaps all the information that falls into a black hole doesn't disappear inside it, but rather gets encoded on the event horizon itself. According to this theory, the black hole's surface would contain all the details about everything that has ever fallen into it. To visualize the holographic principle, it helps to imagine an ordinary hologram, where the depth and details of a three-dimensional image are stored on a flat, two-dimensional surface. In the case of a black hole, imagine that the data about the three-dimensional matter falling into it could be represented entirely on the two-dimensional event horizon. This means that even though matter vanishes from view once it crosses the event horizon, the black hole's surface could retain an imprint of that matter in a way that we don't yet fully understand, reducing the need for a mysterious internal process that could potentially destroy the information. If the holographic principle applies to black holes, it might also apply to the entire universe, suggesting that the three-dimensional reality we experience could be a kind of hologram, with its fundamental properties encoded on a two-dimensional surface at the boundaries of the universe. This holographic universe theory is a bold idea, but it's one that physicists are still investigating and debating. One way scientists have tried to test the holographic principle is by studying the thermodynamics of black holes, particularly through something known as black hole entropy. Entropy, in physics, is a measure of the disorder or information content of a system. Jacob Bekenstein, a physicist who studied black hole thermodynamics, theorized that the entropy of a black hole was proportional to the surface area of its event horizon. This was surprising because entropy usually depends on the volume of a system. But if black holes store information on their surfaces, it makes sense that their entropy would depend on surface area instead. For those who study quantum mechanics, the holographic principle offers a bridge between relativity and quantum theory. The holographic principle suggests that if space itself has a kind of holographic encoding, then gravity could be explained in terms of quantum information. This is a significant step toward reconciling the two theories, possibly leading to a theory of everything. Scientists have explored these concepts using mathematical frameworks such as string theory. In string theory, a hypothetical anti-de Sitter space might resemble the interior of a black hole, and a quantum theory on its boundary would fully describe everything within it. This has led to a groundbreaking idea known as the anti-de Sitter conformal field theory correspondence, frequently abbreviated as ADS-CFT, which proposes that certain gravitational systems could be described entirely by quantum mechanics on their boundaries. Although highly abstract, this correspondence provides a model that closely resembles the concept of a holographic black hole, giving physicists a way to test aspects of the holographic principle in a controlled theoretical setting. While experiments to directly observe holographic black holes are challenging, researchers have developed advanced computer simulations to model how black holes could store information on their event horizons. These simulations use the latest understanding of quantum field theory to explore how particles behave near a black hole's edge. Through these simulations, scientists hope to better understand the encoding process that might preserve information in a way similar to a hologram. If holographic black holes are indeed real, they may solve the information paradox and provide a new perspective on how information behaves in extreme environments. Instead of thinking of black holes as objects that destroy information, we would view them as unique structures that transform information, compressing it into a flat record on their surfaces. This perspective could also inspire new ways of thinking about data storage and computing, where information is preserved in a minimal, compact form, yet retains all the complexity of the original data. The idea that black holes could act as cosmic holograms suggests that what we see as a void or collapse is actually a profound transformation process. This shift in thinking could have profound implications for our understanding of entropy, quantum information, and even the fundamental structure of the universe. If the universe is indeed holographic in nature, it would imply that the depth of space is, in a way, an illusion, a product of information arranged on surfaces. If space and depth are just expressions of information, what does it mean to live in a three-dimensional universe? Interstellar travel and black holes, science fiction, or future reality? Could black holes serve as cosmic gateways to distant regions of the universe, or perhaps even as shortcuts through space and time? Or could their immense gravitational forces act like a slingshot, giving a spacecraft the speed it would need to explore stars and galaxies far beyond our reach? The most straightforward way that black holes could contribute to interstellar travel is through their powerful gravitational pull, which could theoretically be used as a gravitational slingshot. In space exploration, gravitational slingshots already work with planets. When a spacecraft passes close to a planet, it can pick up speed by using the planet's gravity, allowing it to conserve fuel while reaching greater speeds. The gravity of massive bodies pulls the spacecraft into a tighter orbit, and as it exits the orbit, it escapes with greater speed. Black holes are vastly more massive than planets, meaning the slingshot effect would be correspondingly powerful. A ship that passed close to a black hole might achieve astonishing speeds, even approaching a significant fraction of the speed of light. Yet, while gravitational slingshots around planets are relatively safe, black holes come with inherent and extreme dangers. A black hole's gravitational field is so intense that anything crossing the event horizon is lost forever. For a spacecraft to use a black hole as a slingshot, it would have to pass incredibly close without getting pulled inside. A miscalculation by even a fraction of a degree could result in the craft spiraling toward the event horizon. Beyond that, the tidal forces near a black hole are also far more severe than those around planets, which means that even a close pass might be dangerous, stretching and twisting the craft with unimaginable force. Still, the idea of using black holes in space travel doesn't end with gravitational slingshots. Some theories suggest that black holes, particularly rotating black holes known as Kerr black holes, could act as portals or wormholes that connect distant points in space. The concept of a wormhole is hypothetical, first proposed by Albert Einstein and Nathan Rosen as part of Einstein's general theory of relativity. Wormholes are envisioned as tunnels through space-time, where entering one end, could theoretically lead to an exit far away in another region of space, possibly even another galaxy. In theory, certain black holes might form the entrance to such a tunnel. However, to function as a wormhole that allows safe passage, a black hole would need specific properties, such as a stable structure and a rotating ring-shaped singularity, conditions that are still purely theoretical. A typical black hole crushes everything that falls in, reducing it to subatomic particles. For a wormhole to work, it would need to somehow hold its shape and not collapse on itself, allowing something to pass through without being destroyed. Some scientists have speculated that exotic matter with negative energy could stabilize a wormhole, preventing it from collapsing. But this kind of matter hasn't been observed in nature. Even if it exists, creating or gathering enough of it to stabilize a wormhole remains well beyond our technological capabilities. Beyond the stability issues, there is the question of time. Traveling through a black hole or wormhole would involve extreme time dilation. This time distortion could complicate any mission that seeks to use black holes for travel, as the passage of time outside the black hole's influence could be drastically different from what the travelers experience. One fascinating possibility is that if an advanced civilization could somehow harness a black hole's energy, they might be able to use it as a near-infinite power source for interstellar travel. A theoretical black hole drive could involve capturing Hawking radiation or utilizing the black hole's rotational energy to power a spacecraft. By approaching the black hole and skimming its event horizon without falling in, a spacecraft might be able to tap into this energy in a controlled way. Black holes are already difficult to approach safely, but capturing Hawking radiation or rotational energy would require technology far beyond anything we have today. Extracting energy from a black hole would involve capturing and redirecting it, a task that would likely demand complex engineering and precise navigation systems. The idea is fascinating, but for now, remains in the domain of theoretical speculation. The future of black hole research. What new discoveries await? Observing black holes has traditionally been one of the biggest challenges in astronomy. By their very nature, black holes do not emit light in the way that stars or galaxies do. Instead, their presence is detected through indirect methods, by observing the intense gravitational effects they have on their surroundings, such as the way they bend light, affect nearby stars, or emit powerful X-rays as they pull in matter. However, with each new generation of telescopes, sensors, and computational techniques, scientists are beginning to catch a clearer glimpse of black holes and their behavior. One of the most revolutionary recent advancements was the development of the Event Horizon Telescope. The EHT was only the beginning, and its success has inspired even more ambitious projects. Plans are underway to enhance the EHT's capabilities by adding more observatories to its network, which would improve its resolution and allow it to capture images of black holes with even more detail. The goal is to provide sharper and more comprehensive views of black holes' event horizons, capturing finer details of the gas and plasma as they swirl around the black hole's edge. Gravitational wave astronomy is also still in its early stages, but it promises to be one of the most powerful tools for studying black holes. Unlike electromagnetic waves, gravitational waves are not hindered by dust or obstacles in space, allowing them to travel directly from their source to Earth. This means that gravitational waves can provide insights into black holes hidden within dense or distant regions of space that are otherwise invisible. In the coming years, a new generation of detectors, including LISA, the Laser Interferometer Space Antenna, a space-based gravitational wave observatory, is expected to launch. LISA will be more sensitive than Earth-based detectors and capable of detecting lower-frequency gravitational waves, potentially revealing a vast new array of black hole interactions, including the merging of supermassive black holes. Another significant area of research involves the study of black holes in other wavelengths of light, such as X-rays and gamma rays. These high-energy forms of light are often produced by extreme processes near black holes, such as the heating of matter in the accretion disk or the launching of relativistic jets. By examining black holes across multiple wavelengths, astronomers can gain a more comprehensive understanding of the physics at play. Instruments like the Chandra X-ray Observatory and the proposed Lynx X-ray Observatory are designed to study high-energy phenomena in space, offering insights into the life cycles of black holes and the energetic events surrounding them. Beyond new instruments, advancements in computational technology are transforming how scientists study black holes. Supercomputers now allow researchers to simulate complex black hole systems, including their accretion disks, magnetic fields, and interactions with surrounding matter. These simulations are crucial for interpreting observational data, as they provide a model for how black holes are expected to behave under various conditions. Simulations have helped scientists understand how black hole jets are formed and what causes their intense emissions. With the continued growth of artificial intelligence and machine learning, researchers are also developing new algorithms to sift through the enormous amounts of data generated by observatories, making it easier to detect faint signals from black holes or identify patterns that might otherwise go unnoticed. A major focus of future black hole research is to gain a deeper understanding of how black holes grow and evolve over time. Black holes start small, but some grow to enormous sizes. This growth process is not well understood, especially for the supermassive black holes found at the centers of galaxies. One question that scientists hope to answer is whether these black holes formed directly as massive objects in the early universe, or whether they grew over billions of years by accreting matter and merging with other black holes. The James Webb Space Telescope and other next-generation telescopes will enable astronomers to peer back to earlier periods of the universe, potentially capturing images of the earliest black holes and shedding light on how they formed and evolved. In the coming decades, new observations and experimental evidence may provide the answers that our theories are looking for. Missions like the Event Horizon Explorer, a proposed project to send an array of X-ray observatories into orbit, aim to capture high-resolution images of black hole event horizons, further unveiling the structure and behavior of these objects. Other concepts, like building a constellation of telescopes in space, could allow scientists to study black holes in unprecedented detail from multiple angles, creating a three-dimensional view of their interactions with the surrounding universe. As black hole research continues to advance, each new discovery adds an additional piece to the puzzle. The tools at our disposal are expanding rapidly, and with these tools, scientists are poised to uncover secrets that once seemed beyond our reach, bridging the gap between our understanding of the true nature of black holes and their role in the cosmos. What sort of exciting discoveries are you looking forward to? Comment down below, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.